Hi, I'm really happy to welcome you again for mechanics and control of robotic manipulator. So far we have seen actually up to motion dynamics. So in specific we have seen one such method called Lagrangian Euler. So this particular lecture we are going to talk about what you call Newton Euler method. So although actually this method is very popular in rigid body or even vehicle dynamics and all, we will see slightly a different version here because it is iterative one here. So how we can employ that into a serial manipulator, that is what the focus of this particular lecture. So let us see that how we are actually doing it. So in the sense, straight away we are going to talk about Newton Euler method. This Newton Euler method is a slightly a tricky one. So what that mean? So you have actually multiple bodies. So we will be talking about joints. Okay. So in the sense, we will actually go your velocity, acceleration all from the base to end, and then we will actually talk about the forces from the you can say end to base. And while going, you can see that the mass is actually part of link. So the link I is having actually you can say I axis and I plus 1 axis, right. So in the sense, we are not talking about the inertia on a joint. So please be clear, the initial forces are due to the link or the mass which is pertaining. So that we would be clarifying, and then we will actually go the velocity propagation and acceleration propagation from one joint to another joint. Okay. So in the sense, we would be doing 3-stage process. So that 3-stage process is actually what Newton Euler method called iterative one, or you can say iterative Newton Euler method. So now we will go the generalized Newton Euler. So where this is actually based on the linear momentum and angular momentum. The angular momentum would brought from the Euler equation, and the linear momentum brought by the Newton's equation. So now the Newton equation and the you can say Euler equation, the simplified Euler equation we are going to use. So where MAC, so here you can see this AC is the linear acceleration of the mass at centroid. So where I is actually inertial tensor, and omega is actually angular velocity, and alpha is you can say angular acceleration, and mass is actually the link mass. So now based on this equation, what one can actually try to see, we can make a iterative one. So here iterative is actually different. So what that means? So we will actually start. This is the base. Okay. So I am actually trying to show that these are number of bodies. So we can actually see that the base velocities. So angular velocity, or you can say acceleration, all alpha also 0, all are zeros, right. So these all 0. So in the sense, from here I can actually go first frame, second frame, third frame, and fourth frame, fifth frame to n frame, right. In the sense, what I can do, I can actually do outward iteration or forward propagation to compute joint velocities. Okay. So corresponding joint velocities I can calculate with the help of whatever the equation which we derived. In the sense, omega I plus 1 to I plus 1, we know already it is R I plus 1 to I omega I. If it is a rotary joint, it would be added. If it is a prismatic joint, not. So similarly, alpha also you can actually get it. So here what addition will be there? This is actually angular velocity. The similar way, angular acceleration component of previous joint would be there. Further, the current angular velocity, or in the sense current active joint angular velocity, which would be interact with the previous joint angular velocity, because it is the same part of link. So that would give a gyroscopic effect. So that would be added. Okay. So in the sense, what we are trying to do, we are trying to compute the you can say angular velocity and as well as angular acceleration. So you can see the angular acceleration previous joint angular acceleration, further you can see the gyroscopic effect. In addition to that, the active you can say joint acceleration. So these three are actually coming into a picture. If it is actually linear, the linear acceleration which we are interested is actually this. So which would be you can see one with come from the you can say slip acceleration of previous, then you can say tangential, then the radial, which we call centripetal. Some people even uses the Coriolis. The Coriolis will happen only if you have a interaction this. So, in the sense you have a angular velocity and the linear velocity active, in the sense this is having and there is a active linear joint, then this Coriolis will come, otherwise there is no Coriolis component. So, that is what we are actually like trying to show. The same thing I am actually like writing in the prismative joint. You can see prismative joint, the angular velocity is very simple. Similarly, angular acceleration also like would be simple, but the velocity component you can recall, because this would be useful further on. Okay. So, this is the angular acceleration part and this is the linear acceleration part. The linear acceleration part, you can see the slip acceleration added, which is slip on the joint, and you can see the Coriolis acceleration. The Coriolis acceleration is omega of I plus 1 to I plus 1 and d dot I plus 1, but this is d double dot, right. So, you please make it this in your mind. So, if it is a linear joint, there would be two additional component will come further to what you can say the previous joint accelerations all playing a picture. So, now in that sense what one can do, for example, now I take link I. So, link I would be having, you can say, ith axis and I plus 1 axis. So, I can calculate the angular acceleration and linear acceleration, okay. But the mass would be concentrated somewhere, right. So, I assume that this is actually like mass concentrated as a CG. So, here only the inertia force would act, right. So, if you see the acceleration is actually like happening here like this, okay. So, what would be the force acting here? The force would be acting, so just opposite to this, right. So, MACG would be acting. So, similarly alpha, so that you can say the torque would be actually like in this way, right. So, this is what inertial torque. So, these two we need to calculate. So, now what we are doing? We are not doing with joint, we are doing for link. So, in the sense what you need to know? You need to know the link inertial force and moments. For that you need to know the link centroidal acceleration. So, for that what one can do? You can actually like go from any one of the joint. The prefer is actually like forward propagation. So, once you know A I to I, alpha I to I, so you can actually like go to A C I to I, okay. So, that is what we are trying to do. So, you can see inertial force and moment computation of link. So far what we have calculated of joints, please be clear. So, this is of link. So, if you have 4 joints, so how many links would be there? Only 3 links would be there, right, because including ground 4. So, in the middle there would be 3 links. So, for example, you take a 2R serial manipulator, okay. So, how many you can say link? So, the ground, so 2, but in the sense there are 2 moving links, in the sense the centroid would be playing these 2 links, okay. In the sense the link inertial force and moments would be 2 components. So, F you can say in this case F22 and F33 and N22 N33, that is all will come. But how you are actually like denoting, that is different. So, we denote this one. So, this is 1 C. So, in the sense this is actually like 1, that way you can actually like make it. This denotion is actually like we will come the representation or how you are actually like approaching, but otherwise one supposed to know we are calculating inertia forces and moments of a link, where the acceleration we have calculated till the previous slide of you can say joints, right. So, this is joint velocity and acceleration, because several of time the students always confuse. So, why you are calculating additionally one more velocity or one more acceleration? This is just because you are having link which is consists of 2 joints, okay. That is what the idea. We will see in example which is very much clear to you. So, now you can see the inertial force which we need to have the you can say centroidal acceleration, linear acceleration you should know. Similarly, you can actually like calculate what we did the previous, because now it is actually like again already you calculated your acceleration here. So, you are actually like going here. So, then you can see there would be a tangential, acceleration, there would be a radial, and there would be a same acceleration would go across. Since these two are in the same frame, so you no need to actually like do any transformation. That's why you can see there is no you can say rotation matrix on here, right. So the next one is actually like you need to calculate the what you call angular moment at the initial location. So you can actually like see the inertia tensor at centroid you calculate, then you can see that angular velocity and angular acceleration you will calculate these two forces and moments. Okay. So once you do this, so what we can actually like do, you can come back from n, because the end effector, the forces and the end effector, you can say I put E, the end effector moments are actually like known to us. So then we can actually like come backward up to 1, because 1 is the active joint, up to 1 only active joints would be there. If you come to 0, that would be the base you can say support force and moment. In addition to that, what this base force we simply call shaking forces. So whatever is transmitted to the base, whatever transmitted as a moment to the base, that would be shaking moments. So if you actually like go to 0, that so F00 and N00, that would be shaking force and moment. Right now we are bothering about only motion dynamics, we will actually like do it. One simple advantage I want to tell here, so the comparison between Lagrangian Euler and Newton Euler, the Newton Euler would give all three, you can say, axis force component and moment component. So in that sense, when you want to do the structural dynamics or you want to do a design, so these equations would be beneficial. Okay. So that's why we are actually like always encouraged to use Newton Euler rather than the Lagrangian Euler. Okay. But we will be seeing in the next lecture what is the comparison between these two, but anyhow now you can get this idea. So now this is what the equation which is we have, because when you talk about this is the link, so this link would be having Fi, because ith frame, this is actually like Fi plus 1 to I plus 1, but this have a inertia force. Now when you see this point, if you assume that this is a dynamic equilibrium or equilibrium, then these two forces sum suppose to be equal to this, right. So that is what we are writing it here. The same way if you talk about moment, so there is a moment here, so that moment would be having a, you can say, couple happening here, that also will come. So that is what you can see. So this is actually like from the, you can say, fourth going joint, or you can say the joint which is in the front, and this is actually like a centroidal force is actually like how much couple it will generate. Similarly, the end effector force, how much couple it can produce, and this is the initial moment. Okay. So now if you don't have initial efforts, okay, so if you don't have initial effort, it is a static equilibrium. Now if you consider, that would be the dynamic case. Now you are clear, right. So the inertia forces, if you include, that become dynamic case. If you ignore, that would be a static case. It is very straightforward, right. So now we will actually like try to calculate. So what would be the joint torque or joint force? If it is actually like a linear joint, so then the F corresponding to, you can say, that ith joint, the third quantity in the sense z axis component would be your tau I. If it is a rotary, so then the n of 3, the third component of I would be your tau I. Okay. That is what I am writing in a, you can say, proper vector form. So you can actually like see it this. So now this is actually like, you can say, a row vector, and this is actually like column vector. So now if you multiply, that would be coming the third component which is given as a torque, which is a rotary joint. If it is a prismatic joint, so that would be the force vector. So then this would be a joint force. Okay. The third axis or the third component of, you can say, force vector would be your tau. So now we will actually like see one simple example, then we will actually like close this particular lecture. For that we have taken the same picture which we have shown in the previous lecture as Newton, you can say, Lagrangian Euler. The same thing we are using for Newton Euler also. Only thing, this is actually like you have to fix the frame. So I assume that this is the frame arrangement. Okay. So I am actually like keeping it, this is Z01. So this is actually like a theta 1, and this is theta 2, this is Z2, and this is Z3, this is 2, and this is 3, and this is 0 and 1. Okay. So now what one can actually like see where the x-axis go, this is x1 and 0, and this is the x2 and this is x3. Okay. So in the sense, what one can actually like find, you can actually like find the what you call the DH parameter. So the DH parameter, I'll just to show it here for your purpose, because last time I've drawn which is actually like gone out. So this is Z01 and this is Z2, this is Z3. So I'm just to showing it how this x01 goes, this is x2 and this is x3. Okay. So now this is actually like theta 1 and this is theta 2. Right now we assume theta 1 and theta 2 are 0, but that is active joint. So in the sense you can see 0 and 1 are same point, in the sense both distance, so both distance are 0 and both are parallel, the angle is 0, but x0 and 1 are parallel, but there is an active joint, that's why theta 1 is coming, in the sense 0 plus theta 1. Second, similarly there is no angle between z1 and z2, but there is a distance along x1, that is L1, and that is the active joint theta 2, and there is no distance along z axis. So these are 0, right. So now you can see this is actually like passive joint, so only L2 comes. So now based on this, what one can do, we can actually like get the individual transformation matrix. From there you can extract the rotation matrices, okay, and you can actually like extract position vectors. In addition to that, you need one more. What one more? So you need to actually like extract the centroidal location, because you are actually like trying to find out VCI and ACI, right. So because you need to calculate the initial you can say forces, right, Fi. So this ACI you need to calculate, for that you need to know the PCI. In this case, what would be the PCI? So you can see that this is actually like along X. So this is the mass concentrated. So I'll show it here. So what is actually like PC1 with respect to 1? 1 is here, Z1. So this is the first centroidal location. So that is along X1. So in the sense the PC1 with respect to 1 would be X1L 0 0, right. So PC2 with respect to 2, this is 2 C2. So what is this? This is actually like X2. So then it is actually like L2 0 0. Okay. So please be clear. So now for example the centroid is coming here. So then this is actually like LC2. Okay. So now you have a triangular link like this. This is Z2 and your centroid somewhere coming here. So then you can see like this is x axis and this is actually like this is your y axis. So this is down. So what would be the PC in this case? So 2 2. So this would be x and minus y, the value I say, and 0, right. So you be clear. So this is actually like with respect to link. So now that also we are actually trying to find out. So in this case it is actually like PC1 would be L1 0 0, PC2 would be L2 0 0. In this case only 2 link. So 2 link centroidal we have actually like calculated, right. Okay. Once you calculated, then we can go forward. For the forward propagation, we calculate the angular velocity, linear velocity and acceleration. In this case linear velocity is not important, so we will calculate angular velocity, angular acceleration and linear acceleration. Further we will end with linear acceleration at centroidal location. So that is what we are trying to do. So for that we assume that the first case, the linear and angular velocity and angular acceleration 0, and the linear acceleration we have considered with the gravity. Okay. So in the sense this is your serial manipulator 2R, the gravity is actually like on this axis, so which is actually like y. Okay. In addition to that, what the g is minus 9.81, we are going to substitute meter per second square. Okay. So you are clear, right. So now this is the initial, you can say, frame, angular velocity, angular acceleration and linear acceleration. Now we will actually like go for propagation. Further, in order to make it simplification, the end effector forces we are assume 0 and end effector moments also 0. In the sense it is actually like free end. Okay. There is no body is actually like considered. So only these two are there. So it's a free end. So there is no end effector force and moments acting. Okay. So now in that sense we will go to the angular velocity propagation, which is we have done in the last class. So this is what we obtained, and we will actually go to the second. This is also we have obtained, and the third quantity we can calculate. Similarly, we can actually calculate the angular acceleration where the gyroscopic effect is coming. So then you can see the slip, or you can say that corresponding angular acceleration component is coming. So you can actually calculate so all three. Okay. So once you calculate all three, so we can go to the linear acceleration. The linear acceleration would be in this case only rotary joint, there is no Coriolis and slip. So these three would be from the previous joint. So we can actually calculate that. So we can start from 0 to 1, 1 to 2, 3, so that we can actually do it. Okay. So once you have obtained, then you can actually go to centroidal. So centroidal actually we can actually calculate based on the corresponding frame. So if you talk about link 1, so the joint 1 you take and then do it. Okay. So that we can do it. Similarly, AC1 and AC2, then you can calculate the initial forces and moment. In this case, we assume it is a point mass. So in the sense the moment would be 0, initial moment would be 0. Okay. So that is what we can actually see. So these two we can actually calculate. So then we can actually go for the backward propagation. So where we start from the F3 to 3, then we come back to F2 to 2, F1 to 1, we stop. Similarly, N3 2, so N11 we will come back via N22. Okay. So that is what we are actually trying to do. Okay. So these are zeros, but this is actually their initial moment, initial forces. So then you can actually calculate. If you want shaking forces, you can go till 0. Okay. So now similarly moment you can calculate backward, and you can actually calculate up to 1. If you want to know the shaking moments, you go up to 0. Okay. So now we can actually calculate, this is what the tau. So now if you do manually by yourself, so finally you can see that the equation will come as similar to what you obtained in the previous lecture. So this is what the case. So with that you can see that the Newton-Euler method also we have demonstrated. So the demonstration, if we do it in MATLAB, that would be very much beneficial. The next lecture you would be seeing the Newton-Euler method or Lagrangian Euler method, do it in MATLAB, and we can actually see whether the equations are matching with what we have done, and we can show that any complex serial manipulator we can do these two methods. Then you can see that what is the difficulty or the complexity coming one to another method, that we can actually see it in upcoming lectures. So with that I am ending this particular lecture. So until then, see you, bye, take care.